All right, page 156, Earth in Space. The seasons. A common misconception is that the seasons change because Earth's distance from the sun changes. But the fact is that seasons are the result of Earth's tilted axis. Evidence. Earth's distance from the sun does change, but that's not why Earth has seasons. If that were the case, people in the northern and southern hemispheres would have the same seasons at the same time. Instead, seasons in the northern and southern hemisphere are reversed. As Earth moves around the sun, sometimes the northern hemisphere is tilted towards the sun. At other times, the southern hemisphere is tilted towards the sun. All right, so before you go on, why are summers generally warmer than winters? And where on Earth is the tilt of Earth least likely to affect seasons, and why? So think about the shape of the Earth, how it's tilted, and answer those two questions. All right, page 157. How does Earth move? Until a few hundred years ago, most people thought that the Earth stood still and the sun, moon, and stars moved around it. But today, scientists know that Earth itself moves and that objects seem to move across the sky because of Earth's motion. Earth moves in space in two major ways, rotation and revolution. So rotation, the imaginary line that passes through Earth's center and the north and south poles, is the Earth's axis. The spinning of Earth on its axis is called a rotation. Earth's rotation causes day and night, as you can see in Figure 1. As Earth rotates eastward, the sun appears to move west across the sky. As Earth continues to turn to the east, the sun appears to set in the west. Sunlight can't reach the side of Earth facing away from the sun, so it is night there. It takes Earth about 24 hours to rotate once. As you know, each 24-hour cycle of day and night is called an Earth day, a regular day for us. All right, so for Figure 1, draw an arrow to illustrate the direction in which Earth rotates. Then draw a line to illustrate the separation of day from night. All right, so in which city will the sun set next? And then where on the Earth is it noon? And where is it midnight? See if you can look at that diagram and guess what those answers would be. All right, now a revolution. In addition to rotating, Earth travels around the sun. Revolution is the movement of one object around another. One revolution of Earth around the sun is called a year. Earth's path or orbit is a slightly elongated circle or ellipse. Earth's orbit brings the planet closer to the sun in January. All right, so for here, you're going to draw a diagram showing Earth's motions. Include both rotation and revolution in your diagram. Look back at page 157 for rotation if you need it. All right, calendars. People of many cultures have divided time based on the motions of Earth and the moon. They have used the motions to establish calendars. A calendar is a system of organizing time that defines the beginning, length, and divisions of a year. The most common calendar today is divided into years, months, and days. 1 year equals the time it takes Earth to complete one orbit. 1 day equals the time it takes Earth to turn once on its axis. People also divide the year into months based on the moon cycle. The time from one full moon to another is about 29 days, though modern months do not match the moon cycle exactly. All right, the history of the calendar. The Egyptian calendar. The ancient Egyptians created one of the first calendars. Based on star motions, they calculated that the year was about 365 days long. They divided the year into 12 months of 30 days each, with an extra 5 days at the end. All right, the Romans borrowed the Egyptian calendar, but Earth's orbit actually takes about 365.25 days. The Romans adjusted the Egyptian calendar by adding 1 day every 4 years. You know this fourth year as leap year, when February is given 29 days instead of its usual 28. Using leap years helps to ensure that annual events such as the beginning of summer occur on the same date each year. All right, then you have the Gregorian. The Roman calendar was off by a little more than 11 minutes a year. Over the centuries, these minutes added up. By the 1500s, the beginning of spring was about 10 days too early. To straighten things out, Pope Gregory dropped 10 days from the year 1582. He also made some other minor changes to the Roman system to form the calendar that we use today. All right, so at the bottom for assess your understanding. What are the two major motions of Earth as it travels through space? And then which motion causes day and night? And the last one, why do people use Earth's motions to determine units of time? All right, what causes seasons? Many places that are far from Earth's equator and its poles have 4 distinct seasons: winter, spring, summer, and autumn. But there are differences in temperature from place to place. For instance, it is generally warmer near the equator than near the poles. But why? So how the sunlight hits the Earth. Figure 3 shows how sunlight strikes Earth's surface. Notice that near the equator, sunlight hits Earth's surface from almost overhead. Near the poles, sunlight arrives at a steep angle. As a result, it is spread out over a greater area. That's why it is warmer near the equator than near the poles. All right, Earth's tilted axis. If Earth's axis were straight up and down relative to its orbit, temperatures in an area would remain fairly constant year-round. There would be no seasons. Earth has season because its axis is tilted as it revolves around the sun. Notice in Figure 4 that Earth's axis is always tilted at an angle of 23.5 degrees from the vertical. The North Pole always points in the same direction. As Earth revolves around the sun, the north end of its axis is tilted away from the sun for part of the year and toward the sun for part of the year. Summer and winter are caused by Earth's tilt as it revolves around the sun. All right, so over here for Figure 3, the diagram shows how Earth's tilted axis affects the strength of sunlight in different places. So infer, draw a circle around the area where sunlight is most direct. Mark an X on the places that sunlight reaches, but where it is less direct. All right, for Figure 4 on this page, the diagram shows how Earth moves during the year, but it's not drawn to scale. So describe the weather and sunlight in the northern and southern hemispheres in March and September. So you're going to look at March in the northern and southern hemisphere, and then you're going to look at September in the northern and southern hemisphere and describe the weather in those areas. All right, solstices. The sun appears farthest north of the equator once each year and farthest south once each year. Each of these days is known as a solstice. The day when the sun appears farthest north is the summer solstice in northern hemisphere and the winter solstice in the southern hemisphere. This solstice occurs around June 21st each year. It is the longest day of the year in the northern hemisphere and the shortest day of the year in the southern hemisphere. As you can see in Figure 5, the sun rises to the northeast and sets the northwest. Similarly, around December 21st, the sun appears farther south. This is the winter solstice in the northern hemisphere and the summer solstice in the southern hemisphere. The sun rises to the southeast and sets to the southwest. All right, equinoxes. Halfway between the solstices, neither hemisphere is tilted towards the sun. The noon sun is directly overhead at the equator, rises due east, and sets due west. Each of these days is known as an equinox, which means equal night. During an equinox, day and night are each about 12 hours long everywhere. The vernal spring equinox occurs around March 21st and marks the beginning of spring in the northern hemisphere. The fall or autumnal equinox occurs around September 22nd. It marks the beginning of fall in the northern hemisphere. Okay, for Figure 5, solstices and equinox. The diagrams show the apparent path of the sun at the solstices and equinoxes in the northern hemisphere. The sun rises and sets farthest north at the June solstice and farthest south at the December solstice. So draw the sun's path at the equinoxes and the December solstice for the southern hemisphere. All right, for assess your understanding. First one, the noon sun is directly overhead at the equator during a solstice or an equinox. All right, then, what causes the seasons? Last one, predict how would the seasons be different if Earth were not tilted on its axis?